mega projects.
Right.
As well as okay.
Good morning, ladies and gentlemen. I hope all is well. My name is Michael Ibrahim. I'm a PhD candidate at UW Madison, and I'm delivering this presentation on behalf of a dream team that consists of both academicians and industry professionals, from both the contractor side and the owner side. And through today's presentation, I'd like to talk to you about a framework of 5-stream production system for mega projects. But before jumping into the details of the presentation, first let me show you the agenda for how this presentation should flow. First, I'll define the problem that this research tries to tackle, and then I'll touch upon the research methodology that we followed in order to achieve our research objectives, and then I'll report the research findings and then open the floor for discussion and questions. Starting with the problem, our industry is facing a serious challenge with regard to mega projects, and these 3 numbers signifies the seriousness of this challenge. Can any of you guess what these 3 numbers stand for in the context of mega projects? Well, research has shown that 98% of mega projects tend to fail in schedule or cost. And in terms of cost, the average cost increase is about 80%, and there is about 20 months schedule slippage on average for mega projects. And this is a serious problem. However, this only says that our house is on fire. However, it doesn't say why is that. So the logical question to ask now is why? And to answer that, productivity will come into place. The construction industry has been suffering from declining productivity since the 60s. And recent studies shows that this trend continues to be true, while non-farm industries have managed to more than double their productivity. But then again, why is that? And the reasonable answer for that is that on average, the construction worker spends only 42% of their time performing value-adding work, while in some other industries, workers spend about 80% of their time to perform value-adding work. And probably by now you know what I'm doing here. I'm performing the 5 whys. And so in order to answer this 3rd why, we have to go into the research. And there's a significant body of literature that reports factors for this. For example, poor project definition can contribute to that, as well as project change, rework, out-of-sequence construction activities, and many others. And to be able to answer the 4th why question here, you have to look deep into the underlying seam that connects all these parts together. And it wouldn't be a surprise to know that it is the poor communication and coordination that is suffered by the industry. And again, there are the statistics that support this claim. Finally, in order to answer the 5th why, you have to take a step back and consider how the industry have been progressing over time. Back in the old days, there was a master builder. This master builder was the owner, the architect, the engineer, and the contractor. However, with time, specialization begins, and then more specialization took place. While specialization is good, fragmentation is bad. And our structure in the industry inherits the fragmentation structure of the parties. So right now in the field, if a mechanical person has a question and the operation person has the answer, they can't ask the question directly and get the answer. However, the question has to fly over different parties, and then the answer has to fly back until it reaches the person that needs the answer on the spot. And this is valid for almost all construction projects. Now consider mega projects and the inherent complexity of their nature and the inherent specialization that they require. And imagine this fragmentation in that. And it wouldn't be a surprise to know that these 3 numbers are true in the industry. And this is a problem that we try to have a first step in fixing it by introducing a production system that can improve the performance for mega project. So now we move to the methodology part. How we did that? We decided to focus on a project that falls into the successful 2% that managed to be successful in terms of cost and schedule. However, we had 2 conditions for this success. First of all, it had to be complicated yet successful, meaning that it is not successful because it's simple. No, it is complicated. However, they managed to make it successful. And that it is successful in terms of cost, schedule, quality, safety, as well as overall satisfaction of different project parties. And also we had some other conditions in order to choose this project. We needed to have a full buy-in from different project parties that worked on this project, meaning from the owner as well as the contractor. And we needed them to give us full access into the data that they have, into their site, to see the field work and to attend their meetings, to know really what they are doing. And the Van Ness and Geary Campus Hospital project has satisfied all these conditions. So, this is a render of the Van Ness and Geary Campus Hospital project. I'm sure some of you are familiar with it. The project scope is building a LEED silver 15-floor hospital and parking area. In terms of project size, it exceeds 1 million square feet, or in meters squared, it's about 93,000 square meter. The project budget is about $2.03 billion, and the project duration is about 68 months, ending in the first quarter of 2019, so it's ongoing construction. And for those of you who have never been to San Francisco before, Van Ness is the name of street and Geary Campus is another name of street. So this is another picture that shows that the project is a whole block in San Francisco. And actually, this is one of the most crowded areas and one of the most congested cities in the United States. And this is a more recent photo of it, and you can see the traffic in the streets. And this is the normal traffic in this area. So, this project was complicated because of its extremely congested work site, as well as the exacting permitting requirements, keeping in mind it's located in San Francisco, California, which is a seismic active area, and it's a hospital. And also because of its challenging quality requirements. And in spite of that, the performance was just terrific. The project is on schedule with cost performance index, which is earned over actual of about 1.25. So far, the team, or at the time of writing the paper, the team managed to increase its contingency by 28.6% through savings. And also the average worker compensation cost per labor hour for this project was only $0.06 as compared to an industry average of about $1, which is a superior performance. So, we went and studied deeply the production system that was used in this project. It consists of 5 streams: the material flow, the safety flow, the production planning, the built-in quality, and the tracking flow. And each of these streams is... I'm having some technical difficulties, I'm sorry for that. And each of these streams have 5 implementation levels, as you can see. It's setting expectations, for example. Can you help me with that? Sorry about that. There should be a picture here. Okay, it's not a problem. I can dig it up. Now it's good again. Anyway, each of these 5 streams have 5 implementation levels. So just to go in deeper for each of the streams quickly, the first one is the production planning flow, which builds on the last planner system, so that in the first stage, the team sets expectations through identifying the goals that satisfy clients' expectations, and then reflects these goals in the master schedule. And then the team uses the pull technique, as was explained in the previous 2 presentations, in order to establish the major phases of work, while focusing on design and construction phase, agency reviews, long lead items, as well as system turnovers. And then in the 3rd stage, the team develops sequence and flow analysis and defines production areas in order to optimize the takt time principles so that all trades can move through the project at the beat of the same drum. And then in the 4th implementation level, the project team looks ahead in order to avoid any interruption in terms of the planned work to be executed at the time. And then in the fifth implementation level, the team plans and controls daily production through daily huddling and swarming. Moving to the second stream, the material flow. Well, the picture doesn't appear, however, I can take it over from here. At the first implementation level, the team identifies clients' customer expectation and converts them to requirements, while identifying the key people who will be responsible for that. And then the team works on developing a standard process that consistently produces work based on the identified client's expectations. And in the third level again, the team is provided with approved documents and field checklists that help assure conformance with the expectations that were identified in the previous two phases. And then in the fourth one, the team tests the developed built-in quality process. And here the first run studies play a major role in that. And finally, the team ensures that all field workers have all the necessary information developed in the implemented BIQ program. For the tracking flow, the project team defines expectations and then sets goals. And then it goes through the 5 implementation levels as well. And the same for the safety flow. So just to wrap up this production system contains 5 streams, and it promotes system thinking. So you should not look at these 5 streams as 5 silos. Instead, you should look at this production system horizontally. So you should set expectations in the 5 streams together, and then you should develop the process through the 5 streams together, review and optimize, and then move on until the action phase. And with that, I conclude the presentation and open the floor for any question. And I'm sorry for the technical difficulties that were faced in the PowerPoint presentation.